Hello and welcome back. So today I want to continue talking about thermal topics and look at heat sinks. And in particular, look at why heat sinks come in two main varieties. So what I got here is two heat sinks from the same manufacturer, same physical dimensions, same size. Difference being that one is shiny aluminum and the other is still aluminum but painted with some sort of black paint. Now, why is it painted? I mean, it's not for aesthetic reasons. Usually your heatsink will be somewhere inside of a box. And it's not for economic reasons. I mean, this is almost twice as expensive as the non-painted one, so you're not doing this for fun. So if you're curious why you would want to paint your heatsinks, then keep watching. So let's start off by remembering a few things about heat transfer. So first of all, you need two bodies that have different temperature, and in order to get heat to go from one to the other, you need to have a temperature difference between the two. So if both your bodies are at the same temperature, there will be no heat exchange. Secondly, there are three methods in which heat will transfer from one body to the other. If we take the example of a transistor bolted on a heatsink, the first method is through conduction. This is a method in which heat travels through solids or between solids. So from the junction to the heatsink and throughout the heatsink, heat travels through this conduction. Now the second method you might be familiar with is convection. This is where heat goes from the solid to a fluid. So air or oil or water or whatever. And what makes convection special from conduction is that the fluid that is accepting the heat is not static. So if we talk about air, air is a very good thermal insulator. Yet it's very good to cool things. And the trick here is that the air around the heatsink is not static. Once the air heats up, it moves away, and then you have new cold air coming to meet your heatsink. So you have a constant airflow. Now you can have natural convection, so air just moving around because of density differences, or you can have forced convection, so with a fan or something. Now there's a third way, which usually in electronics it's neglected because it's very insignificant, but when we talk about very hot bodies, then this becomes a very important heat transmission method. And what I'm talking about is radiation. So heat transfer through radiation. Now, one of the best examples for this is the heat coming from the sun. There's no air in between the sun and the earth, so there's no convection, there's no other material, so there's no conduction. The only way through which heat can get from the sun to us is through radiation. Now, to get a better understanding of heat transfer through radiation, let's first understand what are the sources of the light coming from an object. So for example, if we have a surface, so this might be a radiator or whatever, the light coming off it has three main sources. So first of all, you have reflected light that is coming from the environment and then bounces off the surface. An extreme example of this would be a mirror. So all the light coming from the mirror has come from somewhere else, it's just bounced off it. Then you have transmitted light, so light that passes through the object, and for this a good example is a piece of glass or your window. All the light coming from the window is actually coming from the other side of the window and it just passed through the window. And finally you have emitted light, so light that the object itself is emitting. Now in the visible spectrum this would be a light bulb or something that's red hot. But in the infrared spectrum, any body that has a temperature higher than 0 degrees Kelvin will emit light in the form of infrared. Now the reason why these three sources of light are important is because there's only so much light that can come from the surface of an object. So the entire light coming from the object is partly the reflected light, partly the transmitted light, and partly the emitted light. And the sum of these three coefficients is always 1. So based on the kind of surface you have, one or other of these parameters will be larger or smaller. So to get a good heat transfer through radiation, the object needs to be able to radiate the heat. So the other two coefficients, the reflected and the transmitted light, need to be as small as possible. So a very shiny object will not be able to transfer heat through radiation because all the light coming from it will be reflected, so it will be coming from somewhere else. On the other hand, a perfectly black body will have no reflected light, no transmitted light, and all of the light coming from it will be emitted. So that sort of body will be the best at transferring heat through radiation. Now this all looks very nice. Let's see how these two things, which have different properties, so one is more reflective than the other, so you can see that this is much more shiny. Let's see how they look when viewed with an infrared camera and when there's certain heat applied to it. So this is basically the setup that I used. I'm powering my two circuits that are placed in series with a current of 2 amps, and the voltage drop on both of them is 10 volts. So there's a voltage drop of 5 volts on each of the circuits. Now, regarding the circuit itself, I don't want to go into too many details. I covered that in the previous video. The only difference this time being that I'm using the TL431, not the TLV431, and that ensures that I have a voltage drop of 5 volts on each of the circuits. So 5 volts times 2 amps, 10 watts on each transistor. Now if we look at this setup in infrared, even without looking at the exact temperatures, we will notice a few things. So we can see that both our transistors are white hot, so roughly the same temperature, but we can also see that the painted radiator seems much hotter than the non-painted radiator. I mean, this is just as blue as the environment, so strictly based on the measurement, it seems that it would be at 20 something degrees, which of course it isn't. Now I tried to make a close-up picture of this to get a clearer view, and I still can't see the temperature of the radiator, but what I can see on the other hand is me taking the photo. So here you can see the camera, these are my fingers, so the non-painted aluminum heatsink works like a mirror in infrared. So basically all of the light coming from it is being reflected from somewhere else. The radiator itself is not very good at emitting its own light. So finally, if we look at the actual temperatures observed on the two heatsinks, we can see that the maximum temperature on the non-painted heatsink is around 116 degrees Celsius, whereas the painted heatsink has only 106. So there's 10 degrees difference between the two heatsinks, which is pretty significant. Now, one of the things to keep in mind though is that using this setup, my airflow, so heat transfer through convection, is highly limited. So usually this sort of heatsink you should put upright so that air can flow through its fins upwards and always get new cold air. If you place it like this, facing down, like I did in my experiment, airflow is highly limited. And under this sort of circumstances, heat transfer through radiation starts to become much more significant than in other conditions. So if I would have been using forced convection, so have a fan blowing over both of these two heat sinks, the temperature difference between the two would have been much smaller. Now, to get a better idea of just how much heat you can actually dissipate through radiation, I found a very nice online calculator. So I will be leaving a link to this website in the description, of course. And if you scroll down through it, you see certain explanations about the phenomenon and so on. And finally, you have this radiation heat transfer calculator. So basically, you need to put in your emissivity coefficient, the temperature of your hot object, the temperature of the surrounding, so the cold object, and finally the surface area of your object. So let's say we have a highly emissive object, 95%, and the area, the surface area, is around 0.0025 square meters, or in other words, 25 square centimeters, so a 5 by 5 square. And under these conditions, you could end up dissipating 1.5 watts, so quite a significant amount. Now, on the other hand, if the heat transfer is much smaller, so you have a very non-emissive surface, let's say a 0.2, so something much more shiny, we drop down to 0.3. So the power that is emitted is proportional to how emissive the object is. Now, I would like to mention one more thing, and that is regarding last episode's experiment. So you may have noticed that the boards were painted in that experiment, and the reason for painting them was to get a uniform emissivity on all of the boards, so on all of the surfaces. But before doing that, I did look at the boards without paint, so the way in which they came from the manufacturer, so from the beginning. And I did make one specific feature on the board that usually doesn't really make sense, and that is this white square on them. And basically this is a square just painted on them through silkscreen, but all the boards have the same paint on them, so the same emissivity. So it's a good way to compare how the rest of the solder mask behaves compared to this silkscreen. So let's look at each board and see what we got. So on the first board, the one with no copper, nothing really interesting pops out. But if we look at a different board, so the red one for example, we see this square showing up. So it's barely visible, it's quite faint, but what this is indicating is not that the temperature here is different than the temperature right next to it, but rather that the emissivity of the surface of the square is different than the one of the solder mask. And since the square appears hotter, it means that it has a higher emissivity than the solder mask. Same can be said about the green board. Again, we can clearly see the square this time, so here the solder mask has a much lower emissivity than the silkscreen. And for example on the black board, we can't see the square. So here the solder mask is almost at the same level of emissivity as the silkscreen. What I'm trying to say by this is that depending on the color and the surface of your solder mask, so of the PCB, you can have better or worse thermal performance. Again, this will not be a highly significant value, so you will not be able to dissipate tons and tons of heat through this method, but this might help if you just need a little bit more power dissipated. And for this, a surface finish that should help the most would not be black paint, but black matte paint. Matte, I don't know how it's pronounced, so not a glossy finish, but rather a non-glossy finish that should be able to radiate much better. But of course, this has to be tried out, so depending on the manufacturer, these paints might have different properties. So it's not as simple as saying, oh yes, black paint is good. No, you need to try it out, see your local supplier what they can offer. So all in all, it's important to remember that if you want to be able to dissipate heat through radiation, the quantity of heat will not be very large, but the way to enhance this is to have a surface finish that has a high emissivity coefficient. If your surface is very shiny, usually this coefficient will be low. So all in all, hope you got some useful information after this. Thank you for watching, leave your thoughts in the comments, make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye!